Cool. Hi, everyone. So yes, my talk is on unlocking network visibility through programmable data planes. So as mentioned, I'm an electronic engineer. For some reason, I enjoy low-level programming, and yeah. So I currently work for Dendrite Cyber, and we are specializing in customized packet processing solutions for high-speed networks. So we have two focus areas. The one is improved visibility into network traffic. So this includes decapsulation of headers, filtering deeper into packets, and improved layer 3 and 4 metrics we expose. And then also network health metrics that we obtain from protocol level from packets. This is with the eye on maybe spotting potential network issues much earlier. So what we'll cover today, I'll first give an introduction on some programmable data planes, its hardware, and also some software and software libraries. And then also discuss a few use cases. We use this for to solve specific problems with the case for network monitoring point of view. So first, some terminology. So since I'm using the word data plane a lot, it's all software-defined networking concepts and components. So the data plane is the forwarding plane. It's the path the packets take. It's the fast path, low latency, no buffering. It's typically through your switching fabric. Then there's the control plane that configures the data plane. This is much slower. It's maybe CPU-based, and it programs the forwarding rules for the packets to take through the data plane. So these two concepts, I see the slides are a bit muddled. So these two concepts can be on a per device. It can span several devices, your data plane and the control plane. The control plane doesn't necessarily even have to be on the same device. So just going through all the technologies. So first, there's fixed function network devices. So these are standard network components, NICs, switches, and routers, and firewalls. It's mostly ASIC-based. They're cost-effective, but they have their limitations. So the features are vendor-defined. It's difficult to customize the workings and reallocate resources inside that hardware platform. They support typical packet header structures, but not support for new types of traffic or header structures and even custom protocols. There's also limited SDN integration sometimes with proprietary interfaces and fixed APIs and software running on them. And then also metrics you get from these devices don't give you necessarily a lot of insight onto what's going on in your traffic. So moving on to programmable data plane technologies, the need for this was driven probably by modern day data center architectures and requirements. So there was a lot of increase in east-west traffic within the data center. So this is mostly due to cloud environments and these days also AI workloads, which are data intensive and require a lot of data to be moved between different servers. CPU also remain a bottleneck for performance, especially for these applications. So you would like to move infrastructure-related networking data movement, you can move to your network device. Also, with changing requirements in the data center, hardware reconfigurability also became a requirement. So programmable network devices can be reconfigured to use the internal resources differently depending on the application that they are required for. Okay, so this is a nice slide. So first is network accelerator cards, basically NICs. I would say modern NICs are basically more towards the middle one, the offload NICs, because you have your TCP offload engines, you check some calculations. It's basically standard features for standard NICs these days. Then you get the SmartNICs. You can see they have a lot of more execution engines. There's some CPU cores, there's programmable pipelines, and there's also a lot of the encryption and decryption that can happen on these SmartNICs. So I've seen with them, some with the CPUs, there's up to like 16 or 64 ARM cores even on some of these cards, which you can even run a fully fledged Linux operating system on it with DPDK on it. So these SmartNICs are also known by lots of different names. You get IPUs, infrastructure processing units. You get DPUs, as data processing units. So it also depends on the use case. IPUs is typical where you do your infrastructure like storage and security offloads. And data processing is where it's more on the ingress side of your server where you want to offload to a specific CPU for further compute. You can offload several CPU-intensive tasks to the SmartNIC. So there's some header parsing you can do, customized header parsing, and traffic classification. You get your security offloads for encryption and decryption, firewalling, and then, there's also storage offload. So the next one. It's one of my favorite devices is the programmable switches. So it basically uses the Intel Tofino ASIC. It's unfortunately end of life. So I have some mixed emotions about this. But there's still some new players in this space. So this is basically a switch with a fully programmable pipeline. So you can describe what happens on the switch. How should the packets be parsed? How should they be processed? What part of the headers do you want to drop? And then also, it is a switch, how it should be routed, load balanced, aggregated, all those things you can do with it. There's a data plane, which is the Tofino ASIC, and then it also usually partnered with some form of CPU. Fortunately, this device, it's a bit of a potato CPU, as one of my colleagues called it. But you can do some control plane functions on it. So the use cases for these switches are typically customized and reconfigurable packet brokers and switches. Also in-band telemetry. So if you have multiple of these, you can get measurements for queue depths as the packets go along, and you can see where bottlenecks are in your system. And then also new protocol definitions you can handle on these switches. And then also just with their reconfigurability, what's quite nice about them is you can have an application server which the switch gets its image from. You reboot the switch, it gets a new image and its new application and its new function, and it can basically do that. So moving to the software side, so what enabled this programmable switch and also starting to be used on more of the SmartNICs is a language called P4. So it stands for Programming Protocol Independent Packet Processors. So it's a lot of P's. It's not Peter Piper picked a peck of pickled peppers. So this is a higher level domain language which basically describes how packets are processed. It's protocol independent. It doesn't care if it's an Ethernet header or what. It just sees bits on a wire, and you tell it how it should process this into in header boxes, basically. So you get P4 compilers for various targets. Like I mentioned, the switch. A lot of the SmartNICs use these compiler for the processing pipeline. There's even targets for program to XTP, and also to eBPF filters, and also to DPDK, although not so well developed yet. This graph also shows programmable switch architecture, which is quite nice about it. You can see, but it's basically the constructs of what the language describes. So you first have your parser that you describe, how it should break up the packets. Then you describe the match action pipeline. So this is what happens to your packet and how it should be processed. So you basically write how the tables and what it looks like, and then the deparser brings everything together and emits it. So then a software-based data plane is the DPDK data plane development kit. So this is a user space C++ library. What makes it special is it basically bypasses the Linux kernel and Linux network stack, and it's optimized for standard NICs like your Intel 7 series, 8 series. It can work with those basic devices. How it works is it basically has a small minimal kernel driver, and it uses a poll mode where it basically polls the device constantly for new packets. Whereas with the Linux kernel stack, you have several interrupts that happens as packets are being progressed through the kernel and to user space. And there's also sometimes packet copying that happens that is expensive and adds latency. So there's some performance stats we have here that we experienced. With the Linux kernel, we could do 1 gigabits per second per CPU core. With DPDK, we could do roughly 10 gigabits per second per core. But this is also a caveat. It depends on your CPU. It depends on how you process the packet and whatever. So with DPDK, it's a highly flexible alternative to the hardware solutions. And what also makes it very powerful is if you use it in conjunction with these hardware platforms for further packet processing. So now from a network monitoring point of view, so there's a growing demand for real-time analytics at higher traffic rates. So you want to see more stats live. You don't want to sample and then process those metrics. Security and health monitoring will also require deeper packet inspection, which requires faster packet processing. So traditional monitoring tools are software-based and will have performance limits, typically, mostly probably on the CPU side. So that is where we want to add a programmable data plane to offload some of that processing to hardware. So with the age-old saying of do what you can in hardware, do what you must in software. So where I have this diagram where your hardware sits with your monitoring side, remember some of these programmable hardware data planes can also be used in line in your network. Okay, so moving on to 2 case studies, use cases we had. So the first one is MPLS decapsulation. So MPLS is a packet routing header that sits between layer 2 and layer 3. So what makes MPLS for us special is the fact that it doesn't show you what the next header type is. You don't know, like similar with IP or with Ethertype, you don't know what the next type of header is. It could be IP, IPv4, IPv6, it could be Ethernet. So we had a use case. We wanted to remove the MPLS headers for better compatibility with a third-party monitoring tool. So a packet broker was initially used, but the packet broker stripped the MPLS headers incorrectly. So a lot of the tools use the first nibble hack that they call. So after the MPLS header, if you see a 4, you can assume it's an IPv4 header. You can check some calculations as well to see the IPv check, if you can spot the IPv4 checksum. If it's a 6, it's IPv6. If it's a 0, you can assume it's a pseudo-wire control word or a MAC address. This works most of the time. So this slide just shows a few different MPLS header constructs. So there's with IPv6 and Ethernet. It's a pseudo-wire control word. There's even MPLS over IP. And then we also had scenarios where we had Ethernet, MPLS, multiple other payloads, maybe Ethernet again, and then another set of MPLS layers. And then also we found that some of the packet brokers we dealt with, we had limitations to how many MPLS labels can be removed. And then also a challenging one was fragmented MPLS over IPv4. So our solution was using a programmable hardware platform to decapsulate the flows in the data plane. So just stepping through it, we parse the header until we reach an MPLS header. Then we say, is there MPLS? If it's no, we can just forward the packet. If there is a header, then we have a lookup table to see how we should decapsulate that MPLS traffic. So if we have a rule how to decapsulate that MPLS header, we can successfully decapsulate it and then send out the traffic without the MPLS header. If we don't, we mirror that packet to the control plane. So in the control plane, we further analyze that packet through speculative parsing to see what header structure is after the MPLS header. So by first looking, you're trying out certain headers. You can see it's the IPv4. You can maybe check for checksum. For IPv6, you have no checksum, so you have to delve deeper and see, is there a protocol, is it UDP, TCP, is there a checksum I can use there? And based on that, you can learn a rule of what does this MPLS stack contain. And then from the control plane, you can program that rule to the data plane, and the packet is then stripped correctly. A second case study is where we did packet duplication on one of these hardware platforms. So deduplication is required when you are sampling traffic from various points in your network towards your monitoring system. So now there's maybe a lot of duplicate traffic. It causes a lot of overhead for your monitoring system and processing software. And might even be, when you have a mismatch of those packets, it might also just cause a bit of confusion. So the idea is we want to remove these duplicate packets. So there are several solutions that are software-based, but it becomes very hardware intensive at high packet rates, since the CPU is once again the bottleneck for processing this. So we also made use of hardware. So just a way of how we decapsulate the packet. So first we pass through the Ethernet packet. We look at the IPv4, IPv6, and so we build up the header stack. Then we look at certain fields in that header to basically calculate a unique signature for that packet. So you can look at the total length. You can look at the header checksum. The header checksum is usually a nice smaller version of the full packet. You can basically a hash over the full packet. You can delve deeper into the TCP header. You have your source and destination ports, a sequence number, which is very helpful. And then you can build up a unique ID for that packet. So you do a calculation over these fields. You ignore certain fields like the TTL, because since you're measuring in different places in your network, the TTL can differ for the same packet. Yes. So we calculate a hash for that packet to get its signature, store it in a hash table. The next time a packet arrives, let's say within a specific given time, it has the same signature, and you store it in that hash table, and there's a collision, then that packet is most likely a duplicate, and we can remove it. So we use the programmable hardware. We offloaded some of these functions that we required for doing this duplication to use the programmable hardware for it. So we used the internal parser to parse the packets correctly. There were certain hardware tools to calculate hash calculations on certain parts of the header, so we can make a unique signature for that packet. And then also there's a lot of SRAM on these devices, so there's we could use that quick SRAM to store our hash table in it. So everything can be done at line rate. So the SRAM is basically the limitation to how many signatures we can store at any given moment in time. And then basically for a given window, we allow a certain amount of packets that we can match to those signatures. So some of the results, I see some of it is a bit moved into the same line. But we had basically 100 gigabits per second of traffic, let's say a packet size of 300 bytes. So this is roughly, I think, if I remember correctly, 40,000 packets. So during a 1 millisecond window, 40,000 packets in a 1 millisecond window, and we successfully dropped 100% of the duplicate traffic. So if you increase the load, let's say we move from 40,000 packets to 200,000 packets during that 1 millisecond window, we successfully started seeing, okay, a decrease in performance, and we started dropping 99.5% of that traffic. So you can calculate with this, basically do an estimate of how much traffic I have, how much duplicates do I see, and then the time window is basically the span between these two, the duration between the duplicates. So yes, so basically just an overview. So the benefits of the programmable data planes, it allows us flexible network packet processing and customized solutions, like I've shown into like these two different use cases. It reduces the CPU overhead of the monitoring tools by offloading the intensive packet processing to the data plane, which in turn improves the efficiency of the network monitoring at high network rates. Thank you. That's it. Thank you for your time.